week's discussion is going to be about X-ray production. So far you've learned about the X-ray circuit and X-ray tube and voltage and current and so on. These first few slides, 1 through 9, are from your textbook, and the subsequent slides are my interpretation of this chapter. Be sure to watch the video and read the chapter. Look at the slides above. Here's a good place to start, though. Once you've done, actually, here's a good place to continue once you've done the prior work. So just to recap, the reason why we have X-rays is because electrons bombard the anode and X-rays come from the anode, right? So a prior question you got in a quiz or homework would be, what is the source of X-rays? That would be the anode. X-rays or X-ray photons are created at the anode. Another question would be, what is the source of electrons? That would be the cathode, right? So electrons are created or released from the cathode filament by thermionic emission and accelerated towards the anode by kVp or voltage. And then once they hit the anode, they suddenly stop, and then we get the magic X-rays, right? So we're going to look at what's happening at the anode. What kind of X-rays are created there? So to understand that, first we got to look at what's happening with the electrons that are approaching the anode. So they have to be traveling at a high rate of speed for us to get the diagnostic X-rays, right? So you learned about energy, and what we need is kinetic energy. Now, something that's heavy will have higher kinetic energy than something that does not weigh as much. Now, electrons are of negligible weight, so we accelerate the electrons at a higher rate of speed, right? So both mass and voltage, mass and speed are directly proportional to kinetic energy. So if it's moving faster, it has higher energy. So we use for the electrons kilovoltage. So this is why we use, say for example, an abdomen X-ray, we might use maybe 80 or 100 kV, and for a hand which doesn't need as much penetration, we use a lower amount, say 45 or 40 or maybe 50, depending on where you're working, right? Because you want to get the electrons moving at a high rate of speed, so they will have a lot of kinetic energy. Now, most of that kinetic energy is converted to heat. Just about 1% is converted to X-rays. So X-ray production is not very efficient if you look at it from this point of view, right? All right, so just to recap a little bit, the electrons are emitted from or released from the cathode, accelerated by voltage, and then they hit the anode. So a typical question you might see on a register review material would be, what are the conditions necessary for X-ray production? That would be a source of electrons, the cathode, a way of accelerating the electrons, the voltage, and a way to suddenly decelerate the electrons, that'll be the anode. Some textbooks include a vacuum envelope, but we're just going to stop here for a little bit and look at what's happening at the anode, right? So the two types of X-rays that we're going to focus on, one is Bremsstrahlung, and the word Bremsstrahlung is a derivative of the German word, means breaking or slowing down. Breaking photon is another way to look at it. So you also learned in prior discussions about charges and how they behave, how charged bodies behave. So electrons are negatively charged, right? Let me get my little pen. Electrons are negatively charged, and protons, which are in here, are positively charged. So a negatively charged body approaching a positively charged body, well, they're going to attract, right? They're going to attract. They're going to attract because opposite charges attract. And because of that attraction, now it's going to lose energy. So this electron coming from the cathode is going to lose energy and give off photons. We call it Brem photons, slowing photons or breaking photon, because of this loss of energy. And so you should know that if the electron was approaching from not so close a proximity, say it was traveling in this direction. Let me change this to yellow. Let's use this yellow. Say it was traveling at this distance from the nucleus. It would still slow down, but because of the distance from now it's at a farther distance from the nucleus, its attraction won't be as strong. So it won't give off the same amount of energy. In other words, it won't lose as much energy in the form of Brem photon. So we can maybe draw it with a longer wavelength. right? Kind of like that. We'll draw it like that, right? So the energy of the Brem photon created is dependent on the proximity of the electron to the nucleus as it approaches the nucleus, right? So that's Brem photons. Again, that's a Brem photon occurs as a result of the proximity of the incoming electron and the nucleus of the target material. All right, the nucleus is positively charged, the electron is negatively charged. Let me erase all this. The next one is characteristic. Now make sure you watch the video. The link is in the notes section of the slide, and this is the video right here. So the incoming electron from the cathode, it can also have another type of interaction. It can eject an inner shell electron. So let's say it knocks out an inner shell electron, as you can see here. Let me get my little razor, my little laser pointer, or a pen. Use a pen. So let's say this is the same incoming electron. It now has enough energy to dislodge the inner shell electron of the target material. So this electron is now knocked off. Now, if you remember, K shell electrons have a higher binding energy, or they're bound to the nucleus with a stronger energy than L shell electrons. So now this L shell is going to say, oh no, there's a vacancy. We got to jump down and fill this gap. The difference between these two shells is given off as a characteristic photon. And it cascades from outer to inner until there's no more vacancy to fill, or there's no more electron that can fill the vacancy. All right, so just to recap, the two types. The first one is an interaction. Bremer is an interaction between the incoming electron and the nucleus of the target material. And characteristic is an incoming electron from the cathode that ejects an inner shell electron of the atom of the target material. All right. Now, most of the photons created at the anode, let me get rid of all of this, are Brem photons. And here's what's happening. Let me first give you an example of this. So imagine you have, let me use, let's say you're in a classroom. Let's draw this. Let's say you're in a classroom, and here is, let's say this is a cake everybody wants to eat, right? Let's call this a cake. Everybody wants to eat this cake. But then there are reams of seats around here. And so then in these seats we have some students who also, maybe they want it, maybe they don't. Maybe they're guardians of the cake. We don't know. We'll just say they're guardians of the cake. They're trying to guard the cake just for argument's sake. So there's maybe 2 here, maybe 2 here, we'll say 4 here. Right? Believe it or not, there's way more space in the atom than it appears on diagrams. So an incoming electron has a greater chance of passing through without making contact with any of these electrons. But it will still have some kind of attraction to the nucleus because it's just a matter of proximity, right? So there are way more electrons from the cathode that will be attracted to the nucleus than will make contact with the electrons of the target material, right? So this is why we have more Brem photons, as in more photons that are released because of the slowing incoming electron, which lose energy, than there are of incoming electrons that will actually eject an inner shell electron from the target material. So let me get my little eraser. So this one would be ejected, right? So he'll be knocked off from its orbit, right? So there are more of these than there are of the cascading ones they'll be giving off. So more Brem than they are characteristic. All right. So, and some textbooks have seen 85 and 15. So 85 Brem, 85% of the X-rays are Brem, and about 15 is characteristic. That's what I've seen in some textbooks. All right, so some factors impact the X-ray beam spectrum, and it should make sense, right? So the type of material that it's made of, and that would mean the atomic number and so on, right? So for example, tungsten. This is a review, by the way. Tungsten has a binding energy of initial electron, binding energy. We're just going to put Be here, not for barium enema, of 69.5. Most of you might remember this. keV. All that means is, let me just go back a little bit so you can use as an example. All that means is, if this was tungsten, the energy that's binding this to the nucleus is 69.5 keV. So if this is hit by a photon or an electron that had the energy of 40 keV, what do you think? Would it eject this binding energy? Pause to see if you could answer this. Would it eject this initial electron with this binding energy? The answer is no, because it doesn't have enough energy to dislodge it. The way how I like to think of this, I think I used this in a review some time ago. Imagine you have, let's say, Sarah. And Sarah has in her orbit, let me go down here and use a different drawing. So let's say Sarah, let's see if I can go to a different screen too. Let's use one that has a white. Okay, good. Let's just use this one. So let's say we have here Sarah. Sarah has in her orbit some other people, and they're closer to her, right? So we'll say, let's draw somebody else. We'll say Sarah's mom is in her orbit. Now let's use sister. Sarah's sister is closer to her. Right, so this is Sarah. And then out here, even farther away from Sarah, we have another person that's out a little bit farther out of Sarah's orbit. We'll say this is her cousin. And then we would say that even farther still is her friend. It's her friend, right? Oh, that's a terrible drawing. You get the idea. And then let me just, for argument's sake, we will draw some shells here. So this is the nucleus, Sarah's family here. We'll just say that's the thing that Sarah's trying to stay close to her family. And she is on the K shell electron, and Sarah's sister is on the L shell electron, or L shell, and her cousin is on the M shell, and her friend is on the N shell. This is KLMN. So Sarah would have the highest amount of energy binding her to her family, and less still would be her sister, less still would be her cousin, less still would be her friend. So it would take less to rip away her friend from the family. Someone could have started a little rumor. Oh, Sarah doesn't like you here. All right. So this person is gone. But if you would take more energy to rip away Sarah from her family, right? You'd have to tell her, I don't know, so that her grandmother ate her goats or something, for her to say, nope, I'm leaving this family. So that's what binding energy is. So let's say we'll say the energy that's required to dislodge Sarah is 69.5 keV. So if the energy that is incident on Sarah is less than that, she won't leave her family. That's what's happening, right? Okay. So that's what's happening. So that's how the target material impacts the characteristic, or the type of photon that's created, because some materials have a lower binding energy, right? So that would result in different characteristic X-rays being created, and so on and so forth. All right. Let me erase all this. Actually, it doesn't matter. All right. So now the last bit we'll look at before we do some go to some practice questions is how KVP and MAS impact the beam. So KVP it primarily impacts the average energy or the quality of the beam. This is a little bit of review for you. And what that means is, so voltage gives the beam its energy, right? So remember that voltage has a bunch of names. Electromotive force is one, or electrical potential difference. I'll just put EPD here. But it's the force that causes electrons to jump around, to move in a circuit, right? That's what's happening. That's voltage causes that to happen, right? So if we have more voltage, then the beam would have more energy because the electrons that are traveling from cathode to anode would have more energy, more kinetic energy. Hence, the resultant X-ray photons created at the anode, they would have more energy. And the reverse is true, right? So KVP is the main determinant of beam quality, and it has a lesser effect on the number of X-rays. So it does have an effect, but it's not the primary determinant of the number of X-rays produced, but it does have an effect. By the way, can you guess what this condition is called? It's a normal variant. Yeah, hopefully you saw this. 1, 2, 3, 4, 5, 6. MAS is the main determinant of the quantity of the beam. So one is quality of the beam, the other is quantity of the beam. MAS has no impact on the quality, but it does on the quantity. Why? Because more MA, remember that MA, milliamp or ampere, is just a unit of current. Unit of current. How much current is flowing in the circuit. And what's current? Just movement of electrons. So more current means more electrons created at the cathode. More electrons mean more photons, more interactions at the anode. That's all that means. That's all that means, right? So MAS is directly proportional to X-ray production, the amount of X-rays produced, right? The effect of MAS is less on the image is less pronounced on modern machines. Well, this might be a review for you, but this is a typical example or a hallmark of dose creep. So you can see here 2.5 MAS yields the same or similar diagnostic quality as the rest of them at first glance. A closer look, you can see, or close examination, you can see that one of these images is more grainy than the other. In any case, this is well within the acceptable range right here. So 2.5, you can up all the way up to 80 MAS, you can still get a diagnostic image. You can still see what's wrong, right? So on older analog systems, it would have a greater effect on the image, but not so much. It has a greater effect on patient exposure and your exposure due to scatter, but not so much on the image. All right. All right. So another thing that affects the quality of the beam is filtration, and so filtration is important because what that does, it removes the low energy photons. Remember that the X-rays are created, and we have all types of it's a polyenergetic beam. So some of the photons are going to be high energy, some's going to be low energy. Think of it like test scores. So someone's going to get 100%, and someone's going to get 60, someone's going to get 40. And let's say you want to raise the average score of these, right? So someone gets 100, someone gets 80, someone gets maybe 75, someone gets maybe 60, someone gets 40. So if we average these out, see if we can average these out, right? So we say 100 plus 80 plus 75 plus 60 plus 40, and we divide that by 5, the average is going to be 71. Okay, now how can we raise the average score here? Well, what if we take away this one? Take away 40. What if we take away 40? All right, let me get this out here. What if we take away 40? Let me go back down here and see if I can draw this. What if we take away 40 and see what we get now. So average before we take away 40 would have been 71. So what happens if we just use the higher energies? So one or higher scores in this case, 100 plus 80 plus 75 plus 60. Now divided by 4. Oh, the average has gone up, 78.5. So that's exactly what's happening with with um, with filtration. Filtration is just removing the lower energy photons. Why would we remove these? Because these lower energy photons would have been absorbed by the patient, but it wouldn't contribute to the useful beam. So we're trying to decrease radiation exposure for the patient. So removing the unnecessary radiation that won't contribute to the useful image. All right. All right, so just to recall, incident electrons or projectile electrons are emitted from the filament, right? The X-ray photon or X-ray particle is created at the anode. The X-ray beam consists of multiple photons of multiple different types of energies. The target material is another name for the anode, where the electrons make contact. All right, so let's go through some practice questions here. Let's first say, what do you remember about Ke, that's kinetic energy, mass, and velocity of an object in motion? You can try to answer these questions on your own. The answers are in the notes section, but you can pause here and try to answer them on your own, right? The next one would be, approximately what percentage of energy from the incident electrons is converted to X-rays and heat? By now, everybody should be able to answer this in unison. What is the force responsible for accelerating electrons toward the anode? And the other one is, what's the other name for Brem photons or Bremsstrahlung X-rays? I won't say them here. You can read these answers for yourself, right? That's if you're looking at the PowerPoint itself, which is on your learning platform. Lecture two recall, and the next bit of questions you can practice is, what are electron shells? Right, I give an example there with your family, right? In the context of electron shells, explain binding energy, how our characteristic X-ray is created. So try to use these questions to test your knowledge, right? What technique is parameters is responsible for beam quality and beam quantity, and why do we use higher kV values for thicker body parts? So this was explained just prior, but the answers are in the notes section of the PowerPoint. I won't read them here, but you could take your time and see if you could figure out what these answers are. All right, so this is the end. The rest of these these slides is reiterating what we just talked about. There is enough information here for you to understand the whole concept. So what you should remember is what's happening with the electrons as they make contact with the anode. And there are two ways that we can have this. It would be Brem photons and characteristic. All right, the last thing we'll talk about here is, so remember earlier I said that KVP is primarily responsible for the beam quality and secondarily responsible for or to a lesser extent it's responsible for more X-rays. All right, well, what's happening? Well, look at this here. You can see this electron has, from the cathode, is passing through the target material, right? So it has, say, 80 kV. This one has 90 kV. Well, because this one has more energy, it has more interactions, hence we get more photons. This one has lower energy, so we have less photons because there's less interaction. We get one characteristic and 3 Brem photons. Here we get one characteristic and 1, 2, 3, 4, 5. So this is a demonstration of how KVP also impact the number of photons. Not the primary determinant, but it does have an impact. And you've also seen this before, the 15% rule. This is basically what it's explaining, 15% rule. We are increasing or decreasing the KVP by 15% will have the same impact as doubling or halving the MAS. So it's not a direct proportional relationship, but it's a directly related relationship. All right, that's the end of it. I'll try to put some activities on and stuff for you to practice with. You can go back and watch this video again and read it. Make sure you read the chapter, and see you in class. Take care.